Okay. So some of the topics that we discussed last class, just going to share it with you, just to recap on what we did last class. Okay. So just before we go there, let me show you what we were discussing last class so that you also aware of what's going on. Okay. Okay. So during our last class, we were talking about these topics. Can you see? So we were talking about something called equations of motion, motion graphs, properties of the motion graphs, scalars and vectors, and resolving vectors. So we managed to cover these areas during the last class. So I'll just run you through the last topics that we discussed last time. So when you say equations of motion, there are four equations that we use. Can you see? These four equations, we use it to do calculations on physics. So these are like the very basics of it, right? So each symbol has its own meaning. So you have learned previously about the O-levels, acceleration and stuff. Okay, right. So acceleration means, change in speed, right, over time. So here we have these symbols. This V, capital V stands for final velocity. That is the last known velocity. That is what we call final velocity. Okay. The U, symbol U stands for the initial velocity, which means the starting speed of yours. Okay. Then again, A stands for acceleration and T stands for time. So these are all standard symbols that we use. Okay. Apart from that, you see this in this equation, S stands for distance, or in other words, we call it displacement. Both are the same. Okay. Then you have the standard symbols again. U stands for initial velocity, T stands for time, and then again A stands for acceleration, and again once again T. They have the same meanings, okay, throughout the equation. So these are four equations that we use to do calculations, right? So when we move on with the questions, we'll understand how to use them exactly. Okay, so don't worry about it. When you do questions, I will explain how to use these equations, and then you will understand how these actually help you out. So coming back to the topics, motion graphs. So here in motion graphs, you have already studied four levels, speed time graphs or distance time graphs, right? So same thing here, just to recap on what we've done the last class. Let me show you a video on what these speed time graphs and distance time graphs are. Okay. So now this is basically a distance time graph, the basics of it. Let's observe.
Distance time graphs, like this one here, allow us to visualize how far something has traveled.
Right.
Distance time graphs, like this one here, allow us to visualize how far something has traveled in a certain period of time. For example, this one here could represent the journey of a cyclist, as well as telling us that she's traveled a total of 50 meters in 11 seconds. Graphs like this also tell us a lot about the different parts of the journey, and you need to be able to interpret each of these different stages. The most important thing to know is that the gradient of the line at any point tells you the speed that the object is traveling at that time. This is because the gradient is equal to the change in distance divided by the change in time, which remember is the formula for speed. So just remember that on a distance time graph, the gradient is always equal to the speed. So for this first section, where she travels 20 meters in 2 seconds, the gradient would be 20 divided by 2.
Okay. So when it comes to distance time graph, the information that you can gain from this graph is one is the distance traveled a particular time. Okay. For example, you can find out at 5 seconds how far you have traveled. Like it's 20 meters, right? Or in 12 seconds, how far you have traveled? 50 meters. So that is the information that you can gather from distance time graph. Apart from that, you can also find the speed, how fast you have been traveling during that specific time. Okay, so generally in a distance time graph, we call this the gradient. Okay, a line and a slope, we call it a gradient. So this one, the gradient tells you that the object is traveling at a constant speed. So always constant speed. Okay, if it's a flat line, can you see here? It's a flat line, right? It's a flat line. This flat line means that what does that mean? The time, the distance remains the same, but the time is going. So what does that mean? Yeah, we call it stationary or not moving, right? Good. And then over here, can you see that it's curving? What do you understand by that? Any idea what this curve means? Now, actually, we said this is actually increasing speed. That means you're accelerating. So the acceleration is actually shown by a curve. If the curve is upwards, we call it acceleration. And at one point, can you see the line is straight, slightly to a certain point? Then it's again moving at constant speed. And finally, it's again curving the other way, downwards. What does that mean? Yeah, which is deceleration. Opposite of acceleration is known as deceleration. Is that clear? All right. So now we want to find the gradient of this for 2 seconds. First 2 seconds, I'm asking what is the speed? Right? To find the speed, you know, in maths you have already done. To find the gradient, we divide the y by the x, right? Y value by x value. So I'm starting from 0. It all the way goes till 20. So that's why I put 20 here. And again, I start the time from 0 and go all the way to 2. So that's why I get 2 seconds. Right? Let's see what it is.
So 10 meters per second. And as it's a straight line, her speed must have been constant through this period. Meanwhile, a flat line, like this one in the middle, tells us that she's stationary, as the gradient, and so the speed, are both 0, which means that she's not moving at all. If the line then gets steeper, the gradient in speed must be increasing, and so this part shows acceleration, while a decreasing gradient shows deceleration.
Exactly.
Now, one really important point is that while the speed is constantly changing, like it is in these last 2 stages, it's a bit trickier to find the speed at any particular point, because we can't just take a total of the entire period, like we did for the first stage. Instead, if we wanted to find the speed at 8 seconds, we'd have to draw a tangent to the curve at that point.
Okay. So when it comes to graphs, now we told if it's a straight line, we can find the gradient by finding the x, y value. Right? But when it comes to curves like this, we cannot just take the gradient of that because it's curving, it's not a straight line. So what we do is we draw a tangent. Okay, you will get used to this when we are starting to do graphs. So when you have to find the gradient of a curve, we draw a tangent. You know what is a tangent, right? Okay, a tangent is basically when there is a curve. Let's say, for example, I want to find the value of the speed. I want to find the speed at 8 seconds exactly. So what I do there is to find the speed at exactly at 8 seconds. At this particular point, can you see this particular point? I draw a line like this so that make sure that it touches this point as much as it can. Okay, I draw a straight line. So when you draw a straight line, just make sure that this gap over here and the gap over around here is the same. Okay, so we'll look at it in detail how to draw tangents and all in later topics. So now we're trying to find the the gradient of this line at this point.
Because remember, a tangent is just a straight line that has exactly the same gradient as the curve does at the point where they touch. And to find the speed, we need to know the gradient. Once we have this tangent, we can calculate its gradient by picking 2 points along the line, like these two, and dividing the change in distance, which is around 12 meters.
Okay, so when it comes to tangent is also like normal gradient. You can choose 2 points within this line. Okay, so you choose a point above and you choose a point below, and then the respective height you can measure. Okay, based on your graph, you can figure out what is the difference between these 2 points. And then you divide it by, again, you come to the x-axis, which is 6, and this is over here, it looks like 9. So the time by x difference, you take it and do the normal gradient method. Is it clear to that?
By the change in time, which is 3 seconds. So we get a speed of 4 meters per second. So to sum up this video, on a distance time graph, straight lines represent constant speeds, flat lines mean stationary, and curved lines represent changing speeds. And if you want to calculate the speed at any particular point, you need to calculate the gradient of the curve at that point. So if the point lies on a straight line, like this one, then you just calculate the gradient of the line by dividing the change in distance by the change in time. If the point lies on a curve though, like this one does, you need to draw a tangent to the curve at that point, and then calculate the gradient of that tangent.
Okay, exactly. So that is all about distance time. Exactly. Okay. Anything else?
Anyway, that's everything for this video.
Right. So that is about distance time. Another type of graph that we were looking at is speed time graphs, or velocity time in other words. Okay, so let's have a look at what
I have had it with trying to organize all my tasks, due dates, and documents across a million different apps. So,
if we want to find the gradient of the curve at any point, we have to do the change in velocity over the change in time, which you might notice is the formula for. In the last video we did, we looked at distance time graphs, which show us how the distance of an object varies over time. In today's video though, we're going to focus on velocity time graphs, which show us how an object's velocity changes over time. These graphs both look pretty similar, and it's really easy in exam to get the two of them confused. So just be really careful and double check which one you're looking at.
Okay. So when it comes to graphs,
as these graphs have velocity.
Okay, when it comes to graphs especially, you have to look at what is your y-axis, this axis. Can you see that they have mentioned its velocity? And you have to write it. Okay, it can be meters per second or kilometers per hour, doesn't matter. You still have to write it. It's very, very important. At the same time, you have to mention the x-axis, that is time in seconds. So especially when you're doing the questions, make sure you read this part. It might be a distance time graph or a velocity time graph. So you have to make sure that you read this part.
On the y-axis and time on the x-axis. If we want to find the gradient of the curve at any point, we have to do the change in velocity over the change in time, which you might notice is the formula for acceleration. So on a velocity time graph, the gradient tells.
Okay, so in this, you remember those symbols I told you, D, U, and all of that? Okay, according to this part, can you see this straight line? What is the initial velocity? What speed does it start at? 0. What speed does it end at? 3. So this 3 is known as the final velocity, and 0 is known as the initial velocity. Understood? So the time here, it has taken, let's say, roughly 2 seconds. It has taken us 2 seconds. So we say change in velocity, that is from 0 you have gone to 3, that is a change in velocity, right? To find the change in velocity, we use final velocity minus initial velocity, which is 0. divided by the change in time, that is the time that you have taken. So that is 2. So when you divide change in velocity by change in time, that is actually the equation for acceleration. So from a velocity time graph, the gradient, can you see the slope? The slope gives you what? Acceleration. In a distance time graph, velocity. Understood? Okay. So when
Tells you the acceleration.
now in this graph, this line means acceleration. What is this part of the line? The flat surface, which has a gradient, 0 gradient. Yes, that means constant velocity. And what does this curve mean? Now, in the previous case, curve means increase, right? Increasing. Now, in this case, what is the gradient here? What is the gradient here? Acceleration. So then this is supposed to be increasing acceleration. Remember that? This part means it's curving upward, means it's increasing. So based on what your gradient is, that will be the same. So this is increasing acceleration. Again, moving at a constant speed and then deceleration coming to 0. Understood? Okay, so let's.
This means that if the curve has a constant positive gradient, like it does in this first section, then it must be experiencing a constant acceleration. Whereas if the curve has a constant negative gradient, like in the last section, then there must be constant deceleration. We can calculate the acceleration or deceleration by plugging the relevant numbers into our equation. For example, in this first section, the change in velocity is 3 meters per second, and the change in time is 2 seconds. So the acceleration would just be 3 divided by 2, so 1.5 meters per second squared. Now, flat sections of the curve have a gradient of 0, and so aren't accelerating at all, which means that their velocity is constant, because it's not increasing or decreasing. So to find the velocity during these stages, all we have to do is look at the y-axis. So in this second stage, the velocity would be 3 meters per second, and in this fourth stage, it would be 5 meters per second. If the curve gets steeper, like in this third stage, the gradient must be increasing. And so this means that the rate of acceleration is increasing as well. The last thing we need to look at is how to find the distance that was traveled. For this, we
Okay. So now you understood what okay. To find the distance traveled in a particular time. So let's say, for example, you are right. So so from there are a few things what loves you can also find the acceleration. Also, you can also find the distance traveled in a particular period of time or for the entire journey. Okay.
need to find the area under the curve. So if we wanted to find the distance traveled in the first 4 seconds, we'd be interested in this area. And to make it easier to calculate, we could split the area up into a triangle on the left and a rectangle. The formula for the area of a triangle is 1/2 base times height. So in this case, that would be 0.5 times 2, which is our time, times 3, which is the velocity. So together, that gives us 3 meters. Then to calculate the area of the rectangle, we have to do base times height. So just 2 times 3, which is 6 meters. So the total area, and thus the total distance traveled, during these first 4 seconds would be 3 plus 6, so 9 meters. One of the odd things to be aware of here is that even though area is usually given in meters squared, because we're finding the distance travelled, we just leave the answer in meters. It's just one of those.
So you might be wondering, okay. So generally area is given in square meter. Right? But in this case, since we are finding the distance traveled, we don't write square meter, then we write in meters because it's distance traveled. But we use this method to identify the distance traveled. Okay? We find the area to find the distance traveled.
Those odd things you have to accept. Now, calculating the area under curved parts of the graph is a bit trickier. And if you only have to estimate it, then you'll be given a grid as the graph background, like this. And you can find the area by counting the number.
Okay. So when it comes to these kinds of things, now can you see there is a curve? So there is no way we can do math and do it, but it's going to consume a lot of time. So instead, what happens is that you will generally be given a graph paper like this. What you can do is you can once again split it into shapes that you like, that you know already, and then or else you can just count the number of blocks. Here 1, 2, 3 like that. You count the number of blocks. Once you count that, you have to make sure. Now in this case, it's fine. This is 1, this is 1. Right? Once you count the number of blocks, you have to figure out how much is 1 square equal. The area of 1 square. Now in this case, it's going to be 1, right? 1 into 1 is
number of squares under that section of.
Understood 1. So then let's say, for example, there are 26.5 squares roughly. Then 26.5 into 1 is supposed to be 26.5. So then you calculate the area as 26.5 meters. But let's say instead of 1 here, it is 2 or 3. Then 1 into 3 is going to be 3. Then 26.5 you need to multiply by 3. So that means each box will have an area of 3 square centimeters, whatever you need based on that into number of blocks you have. Okay.
Of graph. For example, in this graph, each square in the grid is equal to 1 meter of distance travelled. So for our curved section, we've got 6 full squares, 1 square that's nearly full, and these other 2 that are almost half full. For these partially full ones, you want to try and combine them to make a full square. So here we can count these 2 halves as 1 whole. And then if we add up all of our blue squares together, we've got a total of almost 8 squares, which means that the total distance travelled over these 2 seconds would be around 8 meters.
So you can just, this is a rough estimation. Okay, it doesn't have to be exactly the half. Now, for example, you might want, okay, there is no piece here, not a complete half. It's fine. You can consider this as almost 1 square. Here you can assume that these 2 together make 1. Like that, you can add up. Whatever that is whole, you can just say that. The tricky areas you can have to consider them now. This is half and this is half. Can I take this small piece over here and connect it with this and say it's 1? Depends on the occasion. If I can't find any other block that is fit into that, I can assume that it's this thing. Now this is not an exact value. This is just an estimation. So you don't have to worry about it. And at the exam also, they generally give you a range. They won't give you a fixed mark. Let's say it won't be 22.5. They will give you somewhere between 21 to 23. If your answer is within that, you still get your marks. Okay, so they're lenient on that kind of things. But when it comes to exact calculation, you have to do it. But when scenarios like this, you have a chance of doing error margin, we say, within a small range. Is it clear to that?
Anyway, that's everything for this video. So if you enjoyed it.
So is that clear? Okay, then we have another. Now these 2 graphs you have already learned it previously. Now we're going to look at acceleration times. Okay, so this is something new that you will be learning under graphs. Okay, in acceleration time graph, we don't have much. We have very basics. Okay, I'll show you.
All right, I want to talk to you about acceleration versus time graphs, because as far as motion graphs go, these are probably the hardest. One reason is because
Yeah, so generally the acceleration time graphs are just a little complex than the normal speed time graphs. So just pay attention. If there's anything that you can't understand, please let me. All right. Okay. So if you take acceleration, you know there is acceleration, positive acceleration and negative acceleration. Negative acceleration meaning it's decelerating, right? Positive means it's accelerating. So here they have given you a simple example of acceleration time graph. Let's have a look at this.
acceleration just
And
naturally
especially, can you see that? And especially when it comes to velocity distance, displacement time graph, you know they are vectors, right? A vector means they have both magnitude as well as direction. So when you come to those types of graphs, you might find a negative side of it. We won't have a negative side for time because time doesn't exist as negative. But when it comes to velocity, when I say negative velocity, that means the direction has changed. So for example, you are heading towards from here to Bambalapiti, we consider that direction as positive. Then the other side is going to be the negative direction. So that is what is being shown in this graph. Okay, let's see.
is an abstract concept for a lot of people to deal with, and now it's a graph, and people don't like graphs either, particularly oftentimes. And another reason is if you wanted to know the motion of the object, let's say it was this doggy, this is my doggy Daisy. Let's say Daisy was accelerating. If you wanted to know the velocity that Daisy had, you can't figure it out directly from this graph unless you have some extra information. You'd have to know information about the velocity Daisy had at some moment in order to figure out from this graph the velocity Daisy had at some other moment. So what can this graph tell you about the motion of Daisy? Well, let's say this graph describes Daisy's acceleration. So Daisy's going to be accelerating. Maybe we're playing catch. We'll give her a ball. We'll throw the ball. Hopefully she actually lets go when she brings it back. And this graph's going to represent her acceleration. So this graph, if we just read it, it says that Daisy had 2 meters per second squared of acceleration for the first 4 seconds. And then her acceleration dropped to 0 at 6 seconds. And then her acceleration became negative until it was -3 at 9 seconds. But from this, we can't tell if she's speeding up or slowing down. What can we figure out? Well, we can figure out some stuff because acceleration is related to velocity. And we can figure out how it's related to velocity by remembering that it is defined to be the change in the velocity over the change in time. So this is how we make our link to velocity.
Can you see there's a triangle here? That triangle means delta, we call it delta. That triangle means change. The symbol for change is given by the triangle. So when you see a triangle V, that means change in velocity. You see a triangle D also, no? Change in time. Okay. So we're going to look at change in velocity. We know acceleration is equal to change in velocity divided by change in time.
So if we solve this for delta V, we'd get that the delta V, the change in velocity over some time interval, will be the acceleration during that time interval times the time interval itself, how long did that take? And this is the key to relating this graph to velocity.
Okay, now if you look at this, we know acceleration equals change in velocity over time. When I rearrange this equation to make delta be the subject, I get change in velocity is equal to acceleration times time.
Velocity. So in other words, let's consider this first 4 seconds. So between 0 and 4 seconds, Daisy had an acceleration of 2 meters per second squared. So that means, well, 2 was the acceleration meters per second squared times the time was 4 seconds. So there was 4 seconds worth of acceleration. And you get +8. And what are the units? This second cancels with that second. You get +8 meters per second. So the change in velocity for the first 4 seconds was +8. This isn't the velocity, it's the change in velocity. How would you ever find that for this diagonal region? This is a problem. Look at this.
Exactly. This is not the velocity. It is actually change. We don't know what was its starting velocity. We don't know what is its final velocity. But we know the difference between two is only 8. Understood?
If I wanted to find, say, the velocity at 6 seconds, well, the acceleration at this point is 2, but then the acceleration at this point is 1, and the acceleration at this point is 0. that acceleration would keep changing. How would I ever figure this out? Like, what acceleration would I plug in during this portion? But we're in luck. This formula allows us to say something really important. A geometric aspect of these graphs that is going to make our life easier. And the way it makes our life easier is that, look at what this is. This is saying acceleration times delta t. But look at, the acceleration we plugged in was this, 2. So for the first 4 seconds, the acceleration was 2. The time, delta t, was 4. We took this 2 multiplied by that 4 and got a number, positive 8. But this is a height times a width. If you take height times width, that just represents the area of a rectangle. So all we found was the area of this rectangle. The area is giving us our delta v, because area, right, of a rectangle is height times width. We know that the height is going to represent the acceleration here, and the width is going to represent delta t. And just by the definition of acceleration rearranged, we know that a times delta t has to just be the change in velocity. So area and change in velocity are representing the exact same thing on this graph.
So now, in this, the area under the graph, what type of graph is it? This is an acceleration time. So in an acceleration time graph, the area under the graph, okay, the area under the graph is actually the change in velocity. Now, for example, they ask you find the, let's take this part, the 4 to 6 region. If they ask you find the change in velocity during the time 4 to 6 seconds, right? Then what you do is you find the area under that line, which is a triangle. So whatever the value that you get is actually the change in velocity. Is that clear?
Area is the change in velocity. And that's going to be really useful because when you come over to here, the area is still going to be the change in velocity. And that's useful because I know how to easily find the area of a triangle. The area of a triangle is just 1/2 base times height. I don't easily know how to deal with an acceleration that's varying within this formula, but I do know how to find the area. For instance, the area here, though I have 1/2, the base is 2 seconds. The height is going to be positive 2 meters per second squared. And what are we going to get? One of the halves cancel, well, the half cancels with one of the 2's, and I'm going to get that this is going to be equal to 2 meters per second. That's going to be the area. That represents the change in velocity. So Daisy's velocity changed by 2 meters per second during this time. Now you might object. You might say, wait a minute. I'll buy this over here because height times width is just a times delta t. But triangles, that has an extra factor of 1/2 in it, and there's no half up here. How does this, I mean, how can we still make this claim? And we can make this claim because we'll do the same thing we always do. We can imagine, all right, imagine a rectangle here. We're going to estimate the area with a bunch of rectangles. And then this rectangle, and then this rectangle, and you're like, that looks horrible. That doesn't look like the area of a triangle at all. It's got all these extra pieces right here, right? You don't want all of that. And okay, I agree. That didn't work so well. Well, let's make them even smaller, right? Smaller width. So and 4 is if you be this times the change in velocity at one point, then we can find the velocity at any other point.
So is that clear? So that is the third graph that we had, right? So that is what we have in an acceleration time graph. Okay. So we looked at that. So just to give you on the SWAT equations also an introduction. Okay. So this is basically
Surf Excel 10 rupees 5
we have SUVAT, so we just put them in an order and this we call it SWAT for convenience.
If we have a car traveling at a constant speed, we can simply find its speed by doing distance over time. In another situation, this car starts with a certain speed and then it speeds up. This equation wouldn't work now because it's only applicable to an object traveling with a constant speed. We need to use some other equations of motion. Let's define the initial velocity to be u, the final velocity v, and the distance between its starting point and final position is the displacement s. A is the acceleration and t is time. These variables are related by Newton's equations of motion, and there are 4 of them. Number 1, the final velocity is equal to the initial velocity plus the acceleration times time. This makes a lot of sense because this here is the gain in velocity. Another one is v squared is u squared plus 2as. Third equation, s is ut plus half at squared. And lastly, s is u plus v divided by 2 times time. We can also easily explain this equation because this chunk here, u plus v divided by 2, is the average velocity. Let's put these aside and look at an example. A car is initially at rest, and after 5 seconds, it has accelerated to 12 meters per second. We have to find the acceleration. I like to use what's called the toolbox method. We write down all the variables that we know, and these will be our tools. We don't know the displacement, so I'll leave it blank. The car was initially at rest, so the initial velocity is 0. The final velocity is 12 meters per second. Acceleration is what we want to find, so I'll put a question mark next to it. T is 5 seconds. So now I need to select an equation that will only involve u, v, a, and t. I can't use any equations with displacement s involved, so it seems like I can use the first equation. But I need to rearrange it first, making acceleration the subject. To bring u to the other side, I subtract. And to bring t to the other side, I divide. Substituting numbers in from the toolbox, we have 12 minus 0 divided by 5, and that is equal to 2.4 meters per second squared for our acceleration. Let's look at another example. I drop a ball from the top of a cliff, and after 20 seconds, let's look at another example.
Okay, is this clear? So first of all, the first thing is when you get an equation, you have to list down the information that you want. So based on the information that they've given, you have to write the information that you have like this. And then once you figure out and what are the missing ones, that what are you supposed to find here, the acceleration. So there is 2 unknowns. There is s also, this displacement. So right now we are not bothered about equation because in the question they never asked us about that. So we are going to look at equation that does not have s and has what we want. So first we write down the equation and then rearrange it before we substitute the numbers. Okay? Let's look at another one.
I drop a ball from the top of a cliff, and after 20 seconds, it hits the bottom. We want to find the height of the cliff. So essentially, we want to find the displacement of the ball.
Okay, so based on this information, what have they given us? They have given us time, okay. What else did they give us? Have they given us s? Have they given us u? This is the ball is dropped. The ball is dropped. So when you say ball is dropped, the initial velocity is 0. Okay, they have given us u. So we have u. Do we know the final velocity? No. Do we know time? Yes. Do we know the acceleration? What is the acceleration? Which way is the ball falling? Upwards or downwards? Downwards. So when it's falling downwards, who is pulling it down? Why does the ball fall? Gravity. So the acceleration is due to the gravity. Any object that is falling downwards has acceleration due to gravity. How much is gravity then? 10. So we have acceleration also. So they won't give you these. You should know that. So object is falling down means it is having acceleration due to gravity. Clear? So let's see.
Because that is equal to the height of the cliff. Again, using the toolbox method, write out SUVAT, SUVAT. S is what I'm trying to find, so here's the question mark. The ball was initially in my hand at rest, so it had a velocity of 0. I don't know the final velocity of the ball, but I know acceleration due to gravity is always 9.8 meters per second squared on Earth.
So where in locals you have learned that testing because they are going to do the calculation. But here we are using 9.81 or 9.8. That is the exact value. So since we use calculators here, we are going to use 9.8 as the acceleration due to gravity. It's anyways, it will be given on the first page on the exam paper, mentioning what is the value of the acceleration. Okay. So moving on.
The question tells us time is 20 seconds. I can use the third equation, s is ut plus half at squared. This becomes 0 because u is 0. So s is half times 9.8 times 20 squared. giving us a height of 1,960 meters. Here's a summary of what to do when using Suvat's equations. Number 1. Write down all the known variables given by the question. Number 2. Identify the unknown. This is what the question wants us to calculate. Number 3. Select the equation that only involves the variables mentioned in the question. Number 4. If needed, you want to rearrange the equation to make the unknown variable the subject. And finally, substitute the numbers in for your calculation.
Okay, so these are some of the steps that you need to follow when you're using SWOT equations. Okay, is that clear? So that is the first part of our thing that we were discussing in the last class. So we looked at so far, we looked at what is equations of motion. We looked at motion graphs. Then we looked at the properties of motion graphs, that is each graph, what do they represent and all. We looked at what is scalars and vectors. This is what we were talking about. The scalars are basically ones with magnitude and vectors are the ones with what do you call direct magnitude and direction. It's clear? Yeah. Then we looked at something called resolving vectors. Okay. So generally vectors are represented by an arrow. We use an arrowhead like this to represent a vector. The arrowhead will point in the respective direction. Okay, right. And then apart from that, the length of the arrow represents the magnitude. So unless you use a scale, let's say for example, you're supposed to draw a line 10 meters long. We cannot draw a 10-meter line on our paper, right? So we use a scale. You know what is a scale? So let's say for example, 1 centimeter is going to represent 1 meter. Then what will be the length of my leg? 10 centimeters. So I draw 10 centimeters and draw an arrowhead in the direction of the movement or whatever. Understood? So that is how we represent. So length of the arrow represents the magnitude. Okay. Generally, you have learned previously that when there are multiple vectors or forces acting on an object, we resolve them and write it as a single force, isn't it? We call it the resultant force or the net force. Now in A levels, what we'll be doing is, earlier you were only looking at forces either that is horizontal or vertical. Now here we have forces that are at an angle. It can be either the angle from the vertical or from the horizontal, like this. Look at this arrow. This arrow is actually at an angle, right? So we will be looking at forces. Now you will be given only this arrow, okay, with a certain angle. Now this angle this is the horizontal. This side is known as the vertical. So the angle is, they have measured the angle from the horizontal direction. Okay, let's say it's theta. Okay, so this is this diagram. This will be given to you. Now what we will be doing here is, we will break down. Earlier we had multiple forces. We made it into one single force, right? We call it the resultant force. But here we are doing a little different, the opposite version, which means you are given a single force, you will have to find the two other forces. We call it the vertical component. This part is known as the vertical component, and this part is known as the horizontal. Sorry, this part is known as the horizontal component, and this is known as the vertical component. Okay, don't worry, we will look at it. Okay, now this is what you have been given. So you will be resolving, you will be finding this force as well as this force. We call it the vertical and horizontal components. Okay, right. So when it comes to resolving vectors, it's very important. This is what I was telling you about, where we choose a scale which fits into a page. Okay, a scale that can fit into a page. And then you use here, simple example I've given you. Choose a scale which fits to your page. For example, if resolving a resultant displacement of 100 meters, use 1 centimeter is equal to 10 meters. So that the resultant drawing is only just 10 meters high. Clearly mark the starting point and a line to represent either vertical or horizontal direction. This will depend on the angle given in the question. For example, if they say the direction is 30 degrees east of north, so you have to know north, east, west. So they'll just to give an idea of what it looks. Don't worry about the directions. Then finally, carefully measure the angle and start by drawing a resultant vector. So there are two, like you can draw a triangle like this. Can you see? We have drawn this line and then draw the vertical and horizontal vector, just connect it like a triangle. Okay. So resolving vectors, now you have learned for O levels as sine, cos, tan, right? So sine means opposite over hypotenuse. We say SOH. Can you see? Sine opposite over hypotenuse. Cos adjacent over hypotenuse. CH short form. Tan opposite over adjacent. So car we say for convenience to understand without getting confused what these are. Just this thing, but if you are familiar with these, then you don't have to worry about it. Okay. So now this is all what we've done for the previous class with the rest of your friends who they are present in the first session. So these are the topics that we've actually discussed during that time. Okay. There's a question here. Why don't you try that question? Okay, so we looked at scale resolving vectors. Now we're going to look at how to resolve vectors by. So we looked at resolving vectors. There are two ways you can resolve vectors. One method is by resolving using scale drawings. That is where you draw the given vector based on a scale. Okay. Next one we're going to look at is resolving vectors by calculation. This is where I told you that you do sine, cos, and tan, where we will doing a mathematical calculation instead of drawing. This is instead of drawing. There are two ways. One method is by drawing. The other method is by calculation. So the drawing method is very simple. You just draw it as per the given, and then you measure it based on whatever the diagram that you have. Put it back in the scale, and you will get the original values. Okay. So now that is second method is this. Now we are going to find the resultant vector. Okay. How to find the resultant vector? So when finding the resultant vector, you can combine by adding or subtracting them to produce a single vector. Right? This you have already done during your level, where you combine two or more vectors together and produce a single vector, which we call the resultant vector. So to find the resultant vector, there are two ways, like I told you. One is the calculation method, other one is the scale drawing method. Right? So let's look at one by one in detail. So this is where when you're combining combining vectors using a scale diagram. Now I gave you a brief of how you do it. Now we are going to look in detail how it is done. Okay. So when you combine, there are two methods that you can actually draw this based on a scale diagram. One is called the triangle method. The other one is called the parallelogram method. Now to start with, first of all, if you're going with the triangle or the parallelogram method, first one is link the vectors head to tail. Now in a vector, can you see this vector? This is a vector. This is called a vector. In this vector, can you see that this arrowhead is known as the head? The rear end or the end of this is called the tail. So when you connect, when it comes to triangle method, the first thing I told you, link the vectors head to tail. So when you say head to tail, what happens is that in this vector, can you see this is vector A, this is called vector A, and this is supposed to be vector B. Okay. So when you connect these two, this is how they have given us the vectors. We are supposed to connect them in the same way or the same angle they are. So when you connect, it's very important. You connect the head with the tail of the other vector. Right? Head with the tail of the other vector. So can you see here? First of all, link the vectors head to tail. Can you see the head of this vector is touching the tail of that B vector. Also see the direction it is. Can you see it's the same direction as it is? You can't change direction really on. We have to represent it same way. Right? That is the first step. You link the two. Step 2 is from the resultant vector, form the resultant vector from bringing the tail of a toe to the head of B. Tail of A to head of B. Now look, this is the tail of A. Right? This is the tail of head of B. You draw a line connecting these two ends. Right? Those two ends, once you connect it, the direction of this will be, now look at this, this is going in a flow, right? He is going this way, he is coming this way. Your resultant vector will be always in the opposite direction of the movement. It is coming this way, so his head will be, can you see, over here. It will be in the opposite direction. So his resultant vector will be the addition of A and If they're going in the same path, we add them. If they're in the opposite path, we subtract. Is that clear? Now this is what we call a triangle method because can you see it forms a triangle? Clear? So here there was a question here. So that's what I told you. So it says draw the vector C equals A plus B. These are the two vectors given. So this is how we represent. Clear to that? Then the next method that I told you is the other method which is called the parallelogram. Something similar to this only, but a little something is little different to this. Let's see. Once again, you link the vectors. Okay, here you link them head to tail, but here you link them tail to tail. Okay, let's see. First, we'll understand how to do the parallelogram, and then we'll see how do I decide which one to use, whether to use the triangle method or the parallelogram method. So first we'll learn the two, and then we'll see how to do it. Okay. That same thing, the same thing I'm going to do using the parallelogram. Okay. Once again, I have these are the two vectors I have. Okay. These are the two vectors I have. In that case, okay, the two vectors that I have are so here in this case, the two vectors that were given were these. There was one vector going this way labeled A. There was another vector labeled this way labeled B. Yeah. So in this case, right? So in this case, what happened was that the triangle method I told you this was the head of it, and this was the tail. So in triangle method, we connected the triangle method, we connected head to the tail. Head was connected to the tail. But in parallelogram method, it's a little different. We connect tail to the tail, tail to tail. Let's see how. Now in this case, I have this is the vector, which is A. I need to represent it this way. So I'm going to connect it from the same direction as this is. Understood? So this is vector B. Then what you do is you connect some and then you complete the parallelogram. That is, you connect something like this parallel to this and then you connect it like that. Understood? So again, then what happens? You draw result from this corner to this corner. Understood? So that will be, then this is called the resultant vector. Can you see this is going this way, this is going this way. Then which way will the resultant go? It will go this way. Clear? Both are going different directions. He will go in the opposite, sorry, not here. This from the middle. Understood? These two vectors are going either sides. This vector will go from the middle, from the origin. Understood? So this vector will be known as A plus B, or the other one C is equal to A plus B. So this is what we call the parallelogram, where we connect tail and in triangle method we connect it to the tail. So that is about that. Okay, so coming back to the lesson. Yeah, so this is what we're talking about, the parallelogram method. Is it clear? Okay, so moving on. So now there's a question over here. Draw vectors A minus B. Now look at this. It says A minus B. Previously, our B was in that direction, right? When it's minus B, Same thing in the arrowhead will be in the opposite direction. So earlier you had the arrowhead here, now we will have the arrowhead over the other corner. Understood? Is that clear? Or is it too? Sorry? Only the B1 is changed. Look, the symbol in front of A is what? Nothing. That means it's positive. Symbol in front of B is negative B. So it will be negative. Can you see? This is vector B. If it is negative B, it will be in the same direction but opposite arrow. Understood the difference? So here what happened? Reverse the direction of the vector B to make it minus. Is that clear? If there's anything you don't understand, tell me. Okay, so same thing, I'm going to use a triangle method. Once again, in triangle method, remember we connected head to the tail. So can you see the head and the tail is connected? But the arrow, now if you look at the triangle, it's in the opposite side. See, earlier it was this side, now it's on this side. Once again, the same thing, once you draw those, just connect the two ends. After that, what do you do to measure C? You use the same scale as you used earlier. Measure the length of this using a ruler and then multiply by the scale you took earlier. That way you will get the value. Clear? Same thing with parallelogram method. You use the same method. Now the way, make sure you have to connect it tail to the tail of it. But my B is this time this side. So now B is at the bottom end, A is at the top end. Understood the difference? So remember, your resultant force will be drawn from here, this part, from the between A and B. Between A and B only we will be drawing it, not from here. Understood the difference? So here is another method that you can use. Now we looked at how to draw them and do. I told you there were two methods that you can do it, either by drawing it or by calculation. So now we looked at how to draw it using a triangle method and a parallelogram. Next, we are going to resolve the vectors or find the resultant vector using a calculation. So most of the time we will be using this one, which is the calculation method. Clear? Okay. So when it comes to calculation method, this is how we do. Combine the vectors by calculation is a two-step process. So step 1, finding the direction of the resultant using trigonometry. Remember that sine, cos, tan we were using? We are going to use that. Next one is finding the magnitude of the resultant force using Pythagoras theorem. You all remember that the addition of squares of the addition of both sides, square root of it is the resultant, the hypotenuse. So same thing we are going to do here. First, what we do is you are given two vectors A and B. Can you see here? We are going to link it head to tail. Okay, head to tail. Can you see they are given perpendicular? One is vertical, one is horizontal. So it's easy for us to make a 90-degree angle. Okay, you connect it into 90-degree angle, and then like the normal method, you connect the two ends. Once you connect that, using Pythagoras theory, what you do is you use Pythagoras theory, a square plus b square, the addition of those two or the sum of those two, square root of that is only the resultant force, the normal Pythagoras theorem to find the hypotenuse. Clear? Then once you find that, to find the direction, now you know this is the resultant force. To find the direction, this is your angle it makes with the horizontal. Okay, so what I do is I measure this angle, or if I don't know the angle, now look, find in the direction. The direction of the resultant vector is found from angle it makes with the horizontal or the vertical. Understood? So this question should imply which angle it is referring to. For example, they will tell you calculate the angle for the horizontal axis. That means with the horizontal line, you find the angle. Okay, so this is what you call the horizontal line. When the line is like this is the horizontal. So the angle you measure is from this to line. This is what you call horizontal. It's the horizontal. The same line. If I draw a line downwards like this, vertical, the measurement from this line to all the way to this, I need the angle, is known as the angle to the vertical. This is called angle to the horizontal. Understood the difference? From this line, you measure. This is called the horizontal. This is called the vertical. Got it? Right. That is how to actually calculate the angle from the horizontal and the vertical axis. Next one, calculate the angle. So that is what you measure. So for example, let's say you are supposed to calculate. So you know the opposite and the hypotenuse. You can use tan theta. Sorry, you know the opposite and that's it. They have given you A and B now. According to this angle, this is your opposite, right? And this is supposed to be a adjacent. Understood? So you can use tan theta and find the angle. Clear? Similarly, for vertical also, you can use the same. Right. That is clear now. Then here is a question. Can you try this question? Try this question. Okay. You take it down. So it says the swimmer is crossing a river by swimming due north. North is up 2 meters per second. The current flows at east 5 meters per second. So in that case, what is that? The swimmer. Which way is the swimmer going? Let's look at it. Okay. Okay, it says a swimmer is crossing a river by due north at 2 meters per second. Okay, so this is north, south, east, west. Okay, this is what we have. Now what we've been told is that is woman is crossing a river by swimming due north at 2 meters per second. The current flows east at 5 meters per second. So the current is this. So he wants to swim this way. Let's say these are the riverbank. This is my riverbank, two sides. Okay. Now this is the swimmer over here. There's a swimmer over here. He wants to go this way. Okay. He wants to go that way at a speed of 2 meters per second. So the speed is 2 meters per second. This is the speed he wants to go at. But the current means the river is flowing this way. The speed of the current is 5 meters per second east. That means the river is flowing like this way at 5 meters per second. This is what we have, right? They are asking us to determine the velocity of the swimmer's motion. Now basically, I have a vector like this 2 meters per second, and I have a vector like this, which is 5 meters per second. Now, how do I find the resultant? So since I'm not going to draw it on scale, I will use the Pythagoras theorem for the calculation. So it's like this. So assuming they meet the bank at this point. So the board is going like this and reaches the bank, right? This is what you have. The board is going this way. So it will reach the bank. Northeast, no? Ah, sorry. Right. I will be in northeast. Okay, right. So east is going this way, sir. 5 meters per second. Is that clear? Now we need to find the resultant force. So we have a force like this, and we also have a force like this, which is 5 meters per second. Clear? Now, in this case, I'm going to connect these two. So I'm going to draw this way, one on this way, and then this is going to be my resultant force. Okay. So here we don't have to worry about the allocate. We can just connect on this way. Right. So in this case, this is 2, this is 5. Then what is this equal to? Square root of 5 squared plus 2 squared, isn't it? So that is 25 plus 4 is 29. So square root of 29 is the value of this, which is somewhere around almost close to 5 point something, right? So we have what they wanted us to find. So let's see what it is. So on this you can see. So we got 2 of, okay, so we got square root of 29. And then they have also asked, did they ask us for, okay, they have also asked for, let's say, the direction. What direction does it go? Okay, so here we were supposed to connect it this way. They've also asked us the direction of the resultant force. So in this case, the direction will be, I'm going to predict the horizontal. Okay, so this is my horizontal, so this angle theta. Okay, so to find the angle, I have the opposite. This is going to be my opposite, and this is going to be my adjacent. Clear? So I'm going to use tan theta. Tan theta is equal to what? Opposite, which is 2. Adjacent is 5. So 2 over 5. So theta is equal to tan inverse. You can get this on a calculator by pressing shift tan divided by 2 over 5. So the value will be, you will get a certain value. Okay, do you have a calculator? We will have to get one. So we will be using it for the purpose to do calculations. Okay, right. So then, once you do the calculation, this is what you get. You get a value of 0.4. So tan theta is 2 divided by 5, which is 0.4. So tan inverse 0.4 is equal to 21.8. So what happens? The swimmer's velocity is 5.4 and moving at 22 degrees to the horizontal. Understood? So that means he is going this way, like around the riverbank. He is going this way at an angle of 22 degrees from horizontal at a speed of 5.4 meters per second. Understood that? So that is how we do those kinds of questions. Okay, so then moving on, projectiles. Okay, before we go on to projectiles, let me show you a video on projectiles.
Yeah.
Okay, let's look at this.
Procrastination isn't a lack of self-discipline, it's genetic.
Okay.
Hey everyone! In this video, we're going to introduce projectile motion. We'll start with some examples and definitions. Then we'll talk about the difference between one-dimensional and two-dimensional projectile motion. After that, we'll do a quick overview of the kinematic equations. And finally, we'll cover some important things to know when working with projectile motion. So, what are we talking about when we say projectile motion? Basically, it's when an object moves through the air and is only affected by gravity. The object could be moving sideways or falling straight down. The object's initial speed and angle determine its path through the air. This shows up a lot in sports. Sometimes the path of the ball has to be precise. Other times, the ball can have a wide range of motions. We usually focus on a single object, but projectile motion can help us describe other things, like the shape of a stream of water. Those are some examples of projectile motion, but what does the term really mean in physics? Projectile motion is the motion of an object while it's only being affected by gravity and nothing else. Projectile motion only refers to the period of time when the object is moving through the air and it's not touching anything else. So this cannonball is not in projectile motion while it's accelerating inside the cannon or when it's rolling on the ground. It's only in projectile motion when it's in the air. The ball on the right is only in projectile motion between the moment it's released and the moment it hits the ground. We call the object a projectile, and we call the path of the projectile motion the trajectory. Projectile motion is also referred to as free fall, but the terms are sometimes used in different ways, and we'll come back to that later. If we say an object is in projectile motion, then air resistance, or the drag force, is ignored. Basically, air resistance makes the calculations a lot more complicated, and we can still predict the motion pretty accurately by ignoring air resistance. Finally, in projectile motion, the vertical acceleration of the object is 9.8 meters per second squared downwards, represented with the constant lowercase g. This is the acceleration due to gravity. If there's no air resistance, then gravity causes all objects to fall down at the same rate, 9.8 meters per second squared. The horizontal acceleration is 0, which means the horizontal velocity is constant. These might be the most important things to remember about projectile motion, because they determine which kinematic equations and values we're going to use. Now let's talk about one-dimensional versus two-dimensional projectile motion. Here's a few different scenarios that we might see. An object could be dropped from rest, meaning it has no initial velocity, and it falls straight down. It could have an initial upwards velocity, so it moves up and then falls down. It can have an initial downwards velocity, so it falls down. It can have an initial horizontal velocity and falls sideways. And it can also have an initial velocity at an angle, so it has an initial horizontal velocity and an initial vertical velocity.
Okay. So did you understand what is projectile? So projectile is basically, these are all possible projectiles. Okay. So this is the path. So it is falling downwards, or even like throwing a ball down, throwing a ball upwards, things like that, or throwing a ball sideways. So when you throw a ball sideways, it's not going to go straight like this, it's going to take a path like this. We call it a trajectory. The path of the, only when it is passing there, not while you're holding it, it's coming from, like the cannonball. It is coming through that cannon, this thing, not when then. Moment is released from there, projectile, and the path that it takes is called a trajectory. So these are some of the things that we'll be looking. So this is what I was telling you about. This was a force that was given to you at an angle. So here we will be resolving into horizontal as well as vertical component. Okay, so we will look at in detail as we go. Is this partly up to you?
We're going to call all of these scenarios projectile motion, or we might say all of these things are in free fall. The object is in the air. The only thing affecting the motion is gravity, so the vertical acceleration is 9.8 meters per second squared downwards. We're going to say the
One dimensional, we use the sweat equation most of the time, but not that we don't use here also. Here it's called two-dimensional. See why? Because there is motion by direction also, direction also. But here it's only one direction. That is why we call one.
projectile motion, because they move in the vertical and horizontal directions. So we use the x and y kinematic equations and two-dimensional vectors. The term projectile motion might only refer to the two-dimensional projectile motion, and the term free fall might refer to one-dimensional projectile motion. So that's something to be aware of. But again, we're going to call all of these projectile motion and split them up as one-dimensional and two-dimensional. So how do we apply the kinematic equations that we already know to projectile motion? For 1D projectile motion,
Complicate things. Okay. Should give you another video on that. Okay.
Is engineering. In previous video, we learned the concept of a straight line motion from vertically from a third floor building to the ground.
Now this is where he was dropping the object.
In previous video, we learned the concept of a straight line motion, a car moving a horizontal motion along a straight path, and a stone falling from vertically from a third floor building to the
So this is what we call one dimension or one dimensional. It's falling in one, either in the vertically or horizontal.
ground. But now how about if an object experiences moving along horizontally at the same time vertically?
Can you see? At one point when
This kind of motion is called
when he was projecting it, at one point it's moving horizontally, at the point it's coming vertical. So this is what we call two-dimensional. Okay?
projectile motion. In this video, we will learn the concept of a projectile motion. Suppose you're firing a cannon at some angle. The cannonball will follow a parabolic path during its flight before it reaches the ground. We will try to understand the movement of the cannonball. First is its velocity. Initially, the cannonball has initial velocity. This initial velocity can be resolved into its x direction as and y direction as. This means that the cannonball is moving upward while moving to the right. When the cannonball moves upward, the velocity in x direction is constant or the same as the value of, while the velocity along y direction is approaching to 0. When the velocity along y direction is equal to 0, maximum height from the ground, the cannonball continues its parabolic path. During its flight, the cannonball experiences a motion going downward while going to the right. This time the velocity along x direction is still constant, but the velocity along y direction is approaching to the value same as the initial velocity along y direction, but in negative value to indicate that it is going downward until the ball reaches the ground and the velocity is 0. To sum up everything, the velocity along x direction is constant and the velocity along y direction is changing with respect to its position. Initially, the velocity along y direction is when the cannonball reaches the maximum height, the velocity along y direction becomes 0, and the velocity of a cannonball before it reaches the ground is equal to the initial velocity along y direction, but in negative value. This time, let us look at the acceleration. There is no other acceleration governing to this.
What it means here is that now you understand what is a projectile, right? It follows the parabolic path. Okay? Let's say, for example, the same scenario where there is a what you call a cannonball. And the cannonball that is being shot. Okay. So now, let's say this is the cannon we have. Okay, this is shooting a ball. This follows a path like this, right? So in its path, the moment it releases, let's say this is the path of it. So the moment it is released, we call this initial velocity. I'm drawing it in blue. Let's say this is how this path. We call it the I. Let's say initial. And the cannonball is being thrown like this. Like it said earlier, let's say this is the cannonball. The horizontal velocity, dh, we have to go at, initial velocity horizontal. I'll put h here. Initial velocity horizontal. And then we have an initial velocity vertical as well. We will resolve this. Okay. Initial velocity vertical is also there. Okay. Now what happens is that this is the ground we have. Now in this path, what happens is that this cannonball will reach a certain height. Let's say it is the maximum height from the ground. Max height. Okay. So generally, when it is at maximum height, this vertical velocity will become 0. Vertical velocity will become 0. Until it becomes 0, this ball will keep on going up. The moment it hits 0, it will start falling down because of gravity. But because now you might wonder, okay, if it is because of gravity, should it just fall down? No, because this one is already there, right? This one will not change. The horizontal velocity will not change. This way will be the same. So, because there is a force this way, there is initial horizontal velocity, this ball will continue to go like that. Understood? So, this ball over here right now is also having velocity initial horizontal. Until it reaches this point, it will be the same. Whatever the value it was here, you continue to go and fall there. Only thing, this one, the vertical velocity will be 0 and then it starts falling. Now it will start falling due to gravity. This part of the graph is falling due to the gravity. This part of the graph is doing work against gravity. So you are trying to go up, but gravity is trying to pull you down. So we say acceleration here is negative g, negative gravity. Understood? Because it's going in the opposite direction, we say acceleration is negative g. When it's coming down, we say acceleration is positive g. Got it? So that is why this cannonball, though it has the speed, it will reach zero because gravity is pulling it downward. So gradually its speed will decrease and finally it will reach a point where velocity is zero. Until it reaches that point, we call it the maximum height. Is that clear? Understood? Okay, so continue. Let's look at the video again. Now, and also, this one I've already taught in the previous class, and just recap it for you. Now, when you have a force, let's say, for example, like this, there is a force like this. Let's say it's a, there is a force. Okay? Let's say it makes an angle theta with the horizontal. This is with the horizontal. Now, when you resolve this, now we say resolving this, we are going to find the vertical, this is the force H, horizontal component of the force, and the vertical component of the force. Okay. So how do you find a horizontal and vertical is basically this one, if you look at it, this is an easy way. Now look at this, this is how my force is, right? When this is coming down, what will happen to the angle? When this is coming down like this, the angle will reduce or increase. So here, you're coming down. Your angle is, what is about the angle? You are measuring from here to here. Your angle decreases. Normally, when the angle decreases, we take cos. When the angle is decreasing, we say it's cos. When the angle, if I'm moving it the other way, this is going, imagine this is going like, from here it's going like this. So what will happen? Increases. When the angle increases, we say it's sine. Okay? When the angle decreases, it's called cos. When the angle increases, it's sine. Okay? So what is this? F. Then you put F. What is the angle? Cos theta. Your horizontal component will be F cos theta. Your vertical component will be F sine theta. Okay. Now let's see how we became cos and sine. Yeah, normally, for example, let's say they will tell you this is moving at 5 meters per second at an angle of 20 degrees. Then what will happen? This will become 20 cos, sorry, 5 cos. What is the angle? 20, right? 5 cos 20. Then this will become 5 sine 20. Understood. So we will be using this in projector. And let me just explain to you how we got cos and sine. So same thing I'm going to draw here. A theta angle. I gave you that so that now you will understand this part. So this is the same thing I am going to draw a horizontal line and a vertical. This is what we have generally. I'm going to draw a line from this side also, connecting these two. Okay. Now this is making 90 degrees. I know this value, which is F. According to this angle, what is this side? You remember sine cos tan? This side is called the opposite. It's opposite to this angle, so we call it opposite. Remember in a triangle, a right angle triangle, this is the 90-degree side. The side opposite to that, the side opposite to the angle is known as the hypotenuse, or the longest side is known as the hypotenuse. If I have an angle here, the angle, the side opposite to that angle is known as the opposite side. Then the remaining side is known as the adjacent. Same thing if I put the angle here. What is this thing? Huh? This is my hypotenuse. This side, according to this angle, this is going to be my opposite, and this is going to be my adjacent. Clear? So now look at this triangle and tell me what is this side supposed to be? That's supposed to be my opposite, right? Opposite. And this side is supposed to be my adjacent. And this side is supposed to be my hypotenuse, right? Now let's see. Opposite of hypotenuse is what? What is opposite of hypotenuse? It's called sine. So what is the angle here? Theta. So sine theta is opposite over hypotenuse. Then hypotenuse is equal to what? Opposite time, sorry, opposite is equal to what? Hypotenuse into sine theta. Multiply these two, I get opposite, isn't it? Which is this side. Hypotenuse sine times sine theta. How much is my hypotenuse equal to? Yeah, so it becomes f sine theta. Now which side is f sine theta? This side, right? Then if this side is f sine theta, this side is also. So isn't it that this side is? Got it? Similarly, I write cos is equal to what? Adjacent over hypotenuse, right? So adjacent over hypotenuse will give me cos theta. Then adjacent is equal to what? Hypotenuse times, which is equal to hypotenuse. So f cos theta is equal to my hypotenuse adjacent, which is my adjacent. This side. That is my t. Understood the difference? Is that clear? So that is how you calculate. So this is what we call resolving. Okay. Generally, like projectile question, they will tell you, and I take the horizontal and vertical count. Understood? This is what we call resolving vector. So when you do questions, you will understand, and when we practice, it will be. Just put it next to that. That's all. Exactly. Right. So let's just look at this video. As in the cost and sine. Remember this, when you keep practicing, automatically it comes. It's a normal thing. Because we have so much questions to do with it. Now this one you will be using throughout your A levels. So it will be a normal thing, like addition, subtraction. It will become a normal thing once you get hands on it. So let's continue.
But only the acceleration due to gravity, which is equal to 9.8 meters per second squared. This acceleration is pointing downward and is constant during the cannonball's flight. Lastly, for distances, there are only two distances which we should give attention. These are the maximum height, when the cannonball's velocity along y direction is 0, and the distance traveled of the cannonball during its flight. Before we end, let me leave you with this trivia. Did you know that in projectile motion, to have a maximum distance travel of an object, it should be fired at 45-degree angle?
So
that is all.
Generally projectiles something. If you want to throw something very far, the furthest distance you can throw, you have to throw at an angle of 45 degrees. Okay? Even though you throw at higher angle, 60 degrees doesn't matter. It won't go further. So the furthest distance it can go is 45. Nowadays you would have got these bombings and all. So if they're sending a missile from here, from Iran to Israel or whatever, they need to send it at a 45 degree angle. Understood? Then only it will travel a longer distance. Okay. And there are a lot of other things also you have to consider, like the weight or wind speed and all of that. But just to give you an idea, to reach the maximum distance, you have to throw it at 45 degrees. Is that clear? Okay, right. So the rest of it, now you have a basic idea of what is a projectile and how to resolve the vectors. So in our next class, what we will be doing is we will be using, I will explain you the other section of the projectile, and then we will be starting to do projectile questions. So we will be using these calculations, the SWOT equations that you learn, all of that, and we will start the. Is that clear? All right. So that's what.
For now, I hope you learned.
What have we discussed today? Is everything clear what we discussed? Okay, it might be too much at the moment, but doesn't matter. Next class, we will recap all of that, and then let's see how we can actually put these information that we learn into questions and quizzes. All right. Okay.